So it's my pleasure to introduce our next speaker, who is Ettore Zanetti. Ettore joins us from Lawrence Berkeley National Laboratory, where he works on lots of things related to prediction, control, optimization, learning for a variety of building applications. Ettore presented here at this workshop in 2024 on a field demonstration, actually a long-term field demonstration of model predictive control for a commercial building. Ettore, I think, has a presentation in the conference coming up, which will include, I guess, lessons learned from
6 years of MPC deployment on that large commercial building.
So I'm very excited for that, and I think folks who are here for the conference should definitely try to make it to that session if you can. But Ettore will talk to us today about BOPTEST. Ettore, please take. Oh, sorry. Probably turn on the screen monitors here.
Okay. Thank you, Kevin, for the kind introduction, and thank you for having me again. So it's lovely to come to this workshop since I discovered it last time. Today I'm going to present to you about an open source software that we developed at the lab called Building Optimization Testing Framework, or BOPTEST for short. And in particular, its applications on training for education, workforce, and also AI experimentation. Before I start, I'd also like to acknowledge the PI of the project, David Blum, who's my supervisor at Berkeley Lab. Sorry about that. So starting with a little bit of an outline, first I'm going to go into a motivation. I mean, we are all building people, so we know what's the motivation behind these tools and need for training the workforce, but it's nice to get a refresher. And then I'm going to go into the tooling ecosystems. How do we make this possible? What's behind BOPTEST with Modelica and the buildings library, and then real world application of how BOPTEST was used. So starting with the complexity, this figure for Kaplan Inkelman shows different generations of district energy systems, starting from a century ago with the central steam plant, where we had this high temperature system heating up buildings. And then 5 generations later to today, we have ambient loop, Gabor mentioned before, where you can also couple in there waste heat sources like data centers. You can have combined heating and cooling. You can have distributed energy sources, storage, electrical storage, electrical production. These systems are becoming very complex to design and control. And this remains true also at the building level. If you look there in 2000, the study from Adefali and Smith, they were trying to highlight what could be the major control issues in buildings. And one that they found was the key. One that they found was the key issue was programming and implementing those control sequences in real buildings. And if we go to today, actually that's only getting worse, because back then in the 2000s, one representative sequence was for a multivariate system could be the ASHRAE 2006. And in the chart, you have the number of lines of code required to deploy that sequence, which in the hundreds, if not a couple thousand. And then if you look to today, or 2020, when ASHRAE Guideline 36 was published, that exploded already to 50,000 without addressing the main issue of deploying those control sequences. And now today, people are talking about AI, advanced control, MPC, 3D interactive buildings, driven optimization, and all of that without addressing this issue with workforce trainings and best practices, which is a little scary. And so how do we solve that? Well, of course, everybody started from a textbook and learning equations, learning control theory. But then in the end, you get to have experience in real buildings or HVAC labs. The unfortunate reality is that as much as it is great, usually this kind of solution is not truly scalable. It's capped to few concurrent students at the same time on a single piece of equipment. The environment is usually bound by whatever is available in the real building and by the weather and real-time control, which prevents you from testing a lot of scenarios at the same time, especially faulty scenarios, which are the most important for troubleshooting and debugging. And then there could be a safety risk in real building for occupant discomfort or equipment breaking, and in the lab also for equipment potentially breaking. And finally, in real buildings and HVAC labs, usually, unless you're really close to the manufacturer or the vendor, these systems tend to be quite locked, so you can't really control everything that's in there. You are limited maybe to some supervisory control or proprietary protocol that you need to follow. So virtual building comes to the rescue. The Germany generator picture, there is a little cyberpunk with the visor, but the idea is that you can scale up the single piece of equipment to however many you want, or however many buildings you want. So in terms of scalability, you could have as many concurrent users as your cloud instance allows, or as many users as you need. And in terms of environment, if you have the building model, you can deploy that in as many scenarios as you want, with the weather that you want, the boundary conditions, sometimes with faulty conditions, and simulate it at the usually much faster than real-time interaction. In terms of safety, there are no risks since it's a sandbox environment and you can play with it. In the worst case scenario, the simulation will crash. And in terms of hardware ecosystem, at least for BOPTEST, it's a standardized open API, which is well documented and easy to use and integrate. This is all great, but in order for this to work, that virtual building simulator needs to be a fair and accurate, realistic representation of the building, and not just the envelope, but the envelope, the HVAC, and the controls. And that brings us to the second part of the presentation on the tooling ecosystem and the work that we do at the lab. Starting with what is needed to simulate a dynamic system in buildings with a realistic control. Well, even in this simple scenario, we have an hydronic system with a boiler, some valves, a couple of circulation pumps, and then a thermal zone with a radiator. And this is one of the simplest systems you can really have. And even in this simple system, you have the dynamics of the building, of the envelope itself, which can be hours to days, depending on the type of building. Then you have the dynamics of the hydronic part, which is the radiator, the valves, the pump, and the boiler, which is in the order of minutes. And then the PI controllers for those systems, which is seconds. And finally, you can have on-off switches, which are discrete events, which can trigger at any time. And traditionally, historically at least, the first simulation softwares tended to blend the physical modeling, the equations, with the solutions, the numerical solutions for those equations, and to accurately describe all these systems and make it scalable and modular was almost impossible. And so that's where equation-based modeling and programming languages came about. Equation-based programming languages basically decouple what is the equations, the physical systems that you're trying to model with the solver that actually solves those equations. Modelica is one of those languages. It's been around for a long time now, more than 20 years, and it's a pretty mature ecosystem. It's being used actively in many industries, such as power generation, or in the automotive industry, or in the aerospace industry. And lately, in the last decade, I would say, started to be used heavily also in the HVAC industry. And one of the reasons for that was the effort of Michael Vedder and the group at LBL with the development of the Modelica Buildings Library. The Modelica Buildings Library is a collection, an open source repository of more than 3,000 models that can encompasses basically everything under the sun for buildings and HVACs and districts. So you have air-based systems, hydronic systems, heating and cooling plants, thermal envelope models of different kinds, district system, as Gregor mentioned, I did help one of his PhD students in modeling an ambient loop with waste heat recovery. And so this allows you to create your digital twin, your building, your virtual test bench building with all the components from the thermal envelope to the hydronic or aerolic side and the controls associated with that. And if you are using Energy Plus, you don't need to abandon anything you did there. There is a separate project called Spawn of Energy Plus, where basically you can take the templates or the IDF files that you developed and couple them with a Modelica model of the HVAC and controls. There is recent work that at the lab where they're trying to automate the process of generating the Modelica code from the IDF file, but that's pretty prototypical. For now, you will have to take the envelope from the IDF file and manually develop the Modelica models. And that then brings us to BOPTEST. So as I was saying, Modelica is very powerful. It does allow you to model all these things, but it's not easy to navigate. It's a complex tool. It requires multidisciplinary knowledge, because if you can put in there all the drag and drop, all the pieces of the equipment and the control, but then if you don't know how to design a control reliably or size the system properly, you will not have a good representation of a building. Which could be what you want, but not necessarily. And so that's where BOPTEST comes in. BOPTEST is another software that we developed at the lab in collaboration with many partners internationally, and basically provides a repository of reference buildings that were carefully developed by us and other partners, and wraps them up into a deployable, controlled software and time environment. I'm going to go a little bit more in detail than explain what it is, but basically it allows you to avoid using Modelica, knowing Modelica, needing any tools that uses Modelica. The only thing you will need is Docker and Python, nothing more. And apart from that, because BOPTEST started as a benchmarking tool for advanced control, it also provides a standardized set of key performance indicators that are calculated at the end of your simulation and can be used to estimate the performance of your controller. Starting with the test cases, as I mentioned, they are high fidelity models using Modelica or Spawn, and in some of them we also use the recently released ASHRAE 231 for control sequences. So ideally, in a little bit, you could go from the virtual building, the virtual deployment and testing, to translating those control sequences into actual BS control sequences that then go into the real building. And because of the level of detail in the modeling of the HVAC and the control, it's possible to overwrite the supervisory layer like set points, or the local loop controls. If you want to control the, I don't know, the pressure set point differential on air handling unit, you can do that. All the boundary conditions are defined, and there are several different scenarios. For weather, we have also uncertainty estimation based on historical data. And then for electricity prices, usually there are different scenarios from constant to highly dynamic, depending on the test case, which allows you to do more load shifting testing, for example, and carbon emission factors. Usually, these test cases, all of them, come with a pretty detailed documentation. You see an example there in the image in the right, or what could be similar to what a real building is, or what an ideal real building is. We know it's not the case, but ideally that should look like with detailed mechanical drawings with all the sensors available, all the control points available, the thermophysical properties of the building, and also the control sequences implemented. Because so this allows you to not look at the Modelica code at all. You just need to look at the documentation, and then that's your building, and you can interact with it. So far, we have 9 test cases available that cover a wide variety of single and multi-zone residential and commercial building with air-based and hydronic-based systems, with fan coils, VAV, radiant floors, centralized or rooftop units, which basically allow you to model from I want to optimize a thermostat in a house to I want to control this rendering unit of central plant in a large commercial building. The runtime environment is based on Docker or Podman. For those that are not familiar, basically Docker allows you to wrap whatever code and software you want around it, so that when you deploy it, you don't need to install any of that software on your machine or on your cloud instance. And so all the Modelica and Python infrastructure that's behind that simulation framework will come automatically when you download the repository, and you don't need to install anything apart from Docker. And then thanks to a web service style deployment, you can imagine that you can deploy basically as many virtual buildings as you want, or as your computer allows, or your cloud instance allows, and interact with them with native REST APIs that are well documented and pretty easy to use. There is one to spin up a test case. There is one to start to advance the test case, to control the test case, and so on. Apart from the REST API, we also built two interfaces on top of that, which I will show the use later. One is BACnet, where if you have a BACnet device or you have BACnet software that you want to interact with a realistic building representation, you can do that with BOPTEST using BACnet. And vice versa, if you want to train your RL algorithm and you want to use a standardized interface, you can use the OpenAI Gym instead of the existing APIs. And lastly, as I said, BOPTEST originally started for benchmarking, and this is reflected by the standardized set of KPIs that are reported at the end of each simulation run. It's nothing strange. It's the usual numbers that we usually look at, like energy use, energy cost, thermal discomfort, peak demand. Recently, we are working on a new variable that tries to estimate the oscillatory behavior of the controller, which is not, usually it's hard to get from a single KPI number, but it is quite important to evaluate the performance of one controller versus the other. So that's in development. It's a little trickier because depending on the piece of equipment and the building, it's not easy to estimate that in a single number, but we're trying. And then we also have an online dashboard that's not publicly available yet, but the idea is basically to run your simulation, get the results, and together with the publication that can come out, you can also publish those data and those results, and then create a common repository that then people can use. And this is aided by the fact that apart from that KPI calculation, BOPTEST comes with some predefined scenarios for its test case. For example, that could have a 2-week preheating period, or 2-week typical heating or typical cooling. And that allows each control developer to test that test cases in that period with those boundary conditions, so that other people testing a different controller with that same building can compare the results one-on-one, which has been a big pain point in general for literature on advanced control in buildings. And so that leads us to the last part of the presentation, BOPTEST in education and how it was used. I tried to cluster it in 4 different buckets. The first one I've seen and participated in is vocational and O&M training, where building professionals came to us and our partners to get trained into troubleshooting and getting better basically at using the BAS system of their building and analyzing data trends. And then used in the classroom, where students can look at the building dynamic analysis, like running simulations, and see the evolution of the profiles based not just on this baseline simulation, but also trying to tweak the control groups, try to tweak those PID manipulate PID's parameters or change the control sequences and see how the building reacts live to that. And then something that wasn't mentioned, I think the core use for BOPTEST, the original intent, was individual and PhD research, where I'm a researcher. I want to do advanced control. I would like to do mostly that, but instead I spent half my PhD designing a building that's a test bench. BOPTEST. And that can be, of course, applied to any sort of advanced control, like reinforcement learning, MPC. Now we have grid interactive buildings, and there is the possibility to do that too. And finally, some use cases which were used by industry and for AI competitions and training. Starting with the workforce development, the Building Efficiency for Sustainable Tomorrow Center carried out a 5-week course with 26 K-12 facility managers. So these were real technicians and facility managers. They managed some schools, I think, across all California, and they attended this class to not only learn more about BAS training, but also to learn themselves how to do the class so that they could spread it among their own technicians. Because again, the only thing you need is a computer or a cloud server. You don't need any sort of equipment or facility. And so it's easy to scale. The outcome was pretty favorable. In these 5 weeks, they tried several things like testing faulty scenarios. So they were given a commercial building with a rendering unit and VAV systems. And in some cases, there was a set point that was mismanaged. In some cases, there was a damper that was stuck. There were like several typical fault scenarios that you will find. And from analyzing the data and the live trend of the building, they had to understand what was wrong with the building and debug it. And at the end, they had a questionnaire where they were all quite impressed with, like, they liked the fact that the environment was sandbox and they could play around with it without breaking it, but also the fact that it felt real. Like they felt like they were controlling a real building. And that's, I think that's the best feedback that we can get as model developers. And this is an example on the software architecture that was behind it. So at the core, there was BOPTEST with its backend interface, as I mentioned. And then the teacher would also create Python scripts that basically would override the controller and create these faulty scenarios. And then those would be deployed to BugsView3, which is it's an open source building automation system viewer. It's pretty bare-bone, but it's comparable to what you will find in the field. And there, as an example, there is a temperature trend of seeing after you close the damper what happens to the supplier temperature. And this work was published, the software architecture was published initially in Azure conference last year, while the outcome of this training program and the follow-up training programs will be published in the ICEEE summer study. So if you're interested, look out for that. Then a second example is how to use it in the classroom. Unfortunately, at the lab, we don't get a lot of chances to interact with students. So it's great to see that someone else does and uses our tools. And Professor Burgess was kind enough to share his experience. He used the BOPTEST in 2 courses, Autonomous Sustainable Buildings and Digital Twins, an AI for predictive analytics, where he deployed his own instance of BOPTEST on his own AWS, and the students basically could interact with the test case by programming and validate the ID loops, develop MPC, and even reinforcement learnings. And another interesting thing that he tried, I think was very cool, he wrapped the BOPTEST APIs around an LLM, and he had the students interact with them through natural language, like start the test case and then, what is this temperature? And that is also something that we are working on. Which I think it's at that edge that I was talking about with AI and how it can be used today. And then the original and core use of BOPTEST was benchmarking, and now it's used in individual research and PhD studies. BOPTEST development started in 2018, so it's been a while now. And throughout that time, people started to use it. and publish. And so now there are, I stopped counting at 100, but I think it's probably closer to 200. There are around between 100 and 200 papers with test cases used from BOPTEST. And because the test case is the same and the scenarios are comparable, now there is a rich data set of advanced control deployments on the same building with the same testing period, so you can actually compare the performance of those buildings. Because during my PhD, when BOPTEST was not there yet, I would find a study and then another one, but they are different buildings, or even just a different baseline controller, and that gives you a completely different performance. As an example, there is a paper from 2024 that tested several different MPCs, but the star there is a reference MPC from the same test case in the same scenario in a simple scatter plot with like cost versus thermal discomfort in the two typical scenarios, one for peak heating and one for typical heating. And before, I also mentioned that BOPTEST does allow you to lower a little bit the entry barrier. PhD students don't need, at least at the beginning, to master building physics, HVAC modeling, control modeling, modelica simulation before they can actually start deploying and developing their algorithm. Of course, if they have access to the house in Purdue, it's great, but not everybody has that opportunity. And so they can start just working on their algorithm from day zero. And on top of that, I would say BOPTEST development has not been just an effort from IBL, it's been an effort from many partners across, a real international collaboration with several organizations across many countries. And the latest iteration of that collaboration is the IBO Project 2, which not only leads the development of BOPTEST, but also fosters the exchange among researchers and students on advanced control and research. And then we can move to how was BOPTEST used in industry, and in particular in this case, in competitions. One of those IBO Project 2 partners, which was a research institute in Norway, did this competition in collaboration with three commercial partners, where the idea was we will sponsor some money and we will try to crowdsource the development of some reinforcement learning. They didn't have a preference on the approach, but like advanced control algorithms for commercial building that reduce energy consumption and enable flexibility for their specific building architecture. And so they seem to have developed a custom test case, and then they started these competitions where basically a user would register on Codala, which is a platform to run these kind of competitions, and gave a set amount of time to the user to interact with the building, where they will provide the documentation and APIs. And so the participant will have an opportunity to interact with the building as if it were a real building, develop their algorithm and fine-tune it. And then in a second part of the competition, in a different scenario, to avoid using the same model that was trained, to be deployed in the evaluation for the final competition. In a different scenario, this control was tested once, and basically the user would submit not the actual results, but just a test ID, and then the platform could query BOPTEST and get the test results directly from BOPTEST. And this is, everybody's nice, but we want to, avoid cheating, and so that's one way to separate the participants and their control approach from the actual results. And also, in this way, the participant can interact with the building without actually making their algorithm public yet, which was good for privacy on their end, and then they will get a score. I would say this competition was quite a learning experience in terms of how does the software actually scale up when you have like hundreds, if not thousands of instances running at the same time. Cloud costs go up very quickly. That's going to be hard. And then how to use BOPTEST for competitive benchmarking, where, as I said, BOPTEST originally started as a research tool where researchers I guess should have a moral high ground what they deliver, but here instead we need to ensure that there is no cheating involved and privacy is respected. And this work was published by Harald Wollnum, who was the PI for this project at CINTEF. And the last example I want to show you is from BSTEC controls. People that are not familiar with them, they are fairly big control manufacturer and deployment company, and they started using BOPTEST to power their tech demos, customer training, and control product development. They actually have a full webinar that was presented at the website if you're interested in looking what they were doing in detail. And in the picture below, they actually, in their new product demos, where they were showing the new GUIs and the interaction with the building and control product, behind those numbers and temperatures and flow rates that there were, there was a BOPTEST building. And this is just to give you a snapshot of that, where basically they coupled the BOPTEST APIs with their whole software ecosystem and backnet network exchange. And I'm going to go into the details of that, but in the picture at the bottom, they took one of the commercial test cases with a rendering unit and took all the measurement points and control points and compared them with their graphic. And they told us that when trying to tweak or play around with this model, with the control inputs, the responses that they got for the model were very similar to what they would see in real buildings, which I think is, again, great feedback from that point of view, because for them, they need to make sure that that's the case too, if they want to train customers on that. And for us, again, because it means that the models that we developed are realistic enough. They don't need to be perfect, but they are realistic enough to be used as proxy for real buildings. And that brings me to the conclusion of this presentation. So hopefully I convinced you that one tool, the whole pipeline. BOPTEST is a scalable, safe, vendor-agnostic virtual environment that everyone from O&M to PhD researchers and industry can use if they need a high-fidelity building model and a simulation environment. It lowers the barriers and enable AI. This high-fidelity buildings model can be used as proxy for training data to benchmark AI and PC and reinforcement learning. And it is becoming a global standard. There are now, again, a lot of publications on it. So you can compare your results with results on the same test cases that people got in literature and see how you compare. In terms of future work, we have a few things in the pipeline, but I guess two of the main highlights are a new test case on data centers. Data centers became quite a hot topic recently. So we are developing a test case on that. And another questions that we often get is, okay, you have these 9 buildings, which are great, but we want to model our own building. And unfortunately, it can be done, of course, and we are always happy to help. Part of the BIPSA Project 2 community effort is to coordinate the development of these test cases, but it's not easy. Like, it requires a lot of deep expertise in modeling and HVAC and building physics. And so we're trying to improve that with, for example, having templated models for HVAC and controls. So if you want a chiller plant, you just get your chiller plant model and then couple it with an Energy Plus template. And so we're working towards that, and hopefully soon-ish will be available. And also coupling it with generative AI, where we are exploring coding and deployment and development of these models through generative AI tools like Blackboard. So with that, I'd like to thank you for your attention and do a little bit of shameless publicity. If you're interested in trying BOPTEST, there is a QR code for the repository and one for the tutorials. And if you're interested in joining BIPSA Project 2, there is a QR code for that too. I would also like to thank the Department of Energy and the Building Technology Office for their continued support. And with that, if you have any questions, happy to take them.
Okay, we'll start maybe with questions in the room for Ettore. I'm just going to stop share here so we can maybe folks online can see what's happening.
Thank you. Fantastic presentation. I like seeing just how many applications that you all managed to find for BOPTEST. Question about the development of tool itself. I know for all the different applications that we're looking at, there's varying levels of complexity or modeling fidelity that can be used to represent the buildings and the building physics to balance that fidelity with the computational expense. What informed the level of fidelity or of the building physics that you all model?
Yeah, that's a great question. I would say for in general, the level of fidelity that we try to achieve is that the dynamic response of the system to a control change is realistic. So the time constants are realistic. If you open or close a valve, the response of the valve is realistic. The pressure response of the loop is realistic. That is not cheap. That comes at a computational cost. So our biggest test case, which is a large commercial building with I think 15 like 100 zones, but simulated through 15 zones, and as I don't know 300 400 measurement points, takes about a couple hours to simulate a full year. But if you want to simulate like 2 weeks or like shorter periods, then it's in the order still of like an hour, less than an hour. So it's not too bad. It's not CFD. Let's put it that way. But it's still not super fast.
Thank you so much.
Sure.
Very nice presentation. Thank you. It's good to see all the capabilities of this BOPTEST and all the software related to it. But I have a general question about the controls itself. Like, do you think at this stage or in future, BOPTEST or any other related software can really replace field deployment, in the sense that in real deployment, field demonstration, you have things related to scalability, costs related to like labor's time and things like that. How do you think BOPTEST could handle that?
Yeah, I mean that's a great question. The short answer is no, of course not. It can, like, there are a lot of practical issues, honestly, that when I try to do field deployment, like data that was mismanaged and drawings that didn't make any sense, and like all that stuff comes on in real building. In BOPTEST, we are trying to implement some of that. Like, for example, for weather, we have uncertainty on the forecasts, which is based on historical certainty and forecast data that we got from like a lot of partners. And we're also trying to implement uncertainty on sensors and potentially faulty scenarios. So we are inching towards that level of realism, and I think that's the long-term objective of the project. And ideally, that helps lower the time that then it takes you to go from the algorithm ready for there to the field deployment. But yeah, in the end, you still have to put it on the ground. So
yeah, thank you.
But I don't know.
You can
Go ahead.
Thank you for presentations. It's very nice to see this alternative related with the BOPTEST. My question is there any near future integration or hybrid simulation with other tools? For example, if I have a very detailed model of a compressor about, but I want to communicate with the system point of view, is there any way to basically copy them?
Sure. I mean, again, BOPTEST is a co-simulation environment. So you can either couple it through BOPTEST. You can use the technology underlying BOPTEST, which is FMI and FMUs, which is basically a binary version of that code. So you can definitely do it. There are several pathways where you can do that.
Yeah, because normally you see, for example, communication between simulating, simulating, simulating,
Yeah, that's definitely possible. And we do. We have projects now where we're trying to couple BOPTEST with like grid simulators, for example, to simulate the impact of several buildings on the grid. So you can definitely do that. Yeah, sure.
I'm trying to understand the architecture of this platform, right? So my understanding is you have the Docker image with all this pre-installed software in there, right?
Yes.
And so for this software that you have installed, pre-installing this image, do you have, for example, Open Modelica? I know that you talked about Modelica.
No, okay. Yeah, I didn't go into too much detail there, but basically all the models come pre-compiled into FMUs. So the Modelica tool is not necessary to run the models even in the Docker.
Okay.
Because they are pre-compiled. By default, we are using Dymola, just because we are testing with all the tools, Daimler, Modelica, Modelon, but we are using Daimler mostly because they have been the most reliable so far. OpenModelica is great, and it's a great open source alternative, but especially for the more complex building, like the one I was mentioning before, unfortunately, it's not there yet. It's too slow and clunky for FMUs. It can simulate them, but not export the binary. Yeah.
So in that case, is that right? Is that the case that, for example, if I want to modify this one component in this multi-zone building, I really cannot, I don't have the flexibility?
No, you can. The Modelica code is there. It's just like there is the code and there is the binary. So you can modify the code, recompile the binary, and then deploy BOPTEST. That's usually how the development of the test case.
Okay, that's great. And then on the building side, do you have Energy Plus or do you have?
Depends on the test case. Some of them, well, most of them actually use Modelica. So it's envelope for Modelica and HVAC can control Modelica. The big building instead of a spawn model, so it has IDF file, Energy Plus on the envelope side. Anything that's not envelope instead is in Modelica.
So then, for example, if I want to do this customized application simulation, then the workflow is I'll just download this Docker image, have that ready, and then modify the Modelica code, and then
compile it and deploy. Yeah, that's right. Yeah.
Following on question, any of the lessons to access the platform?
No, it's open source. BOPTEST is.
Because in use for that, Damola within license.
Sure, yeah, that's the, so you can use OpenModelica, which is open source, but that would allow you to only develop more simple models. If you want to develop something more complicated, you probably would need a Modelica tool with a license. Or honestly, BOPTEST is not specific to anything Modelica, it's just FMUs. So you could use MATLAB or any other tool that supports FMU export. We never tried it, but if it's an FMU, it will work. Technically.
So then I'm sorry, just one quick last one. Then the Docker image, my understanding is it just includes all these 10 or 9 test cases in there. So that's kind of comes in.
Yeah, it includes the test cases, it includes the Python code that coordinates the simulation and handles the controls and does the management with APIs and the KPI calculation, and also the worker management, like if you want to deploy multiple test cases and something like that. Yeah, sure.
I'm sorry if I missed this, but did you test this software against natural building?
Most test cases started as real building models that then were validated against those. Not all of them, but most of them.
So you're confident in the controls and the response?
Yeah, we're kind of like the control sequences that are implemented. There is a bit of variety because again, the community is quite international, so it's interesting to see the different standards. Like we have a building in France with an hydronic system and their control protocols, and then we have here air-based system with Ashroid, but all of them are based on realistic control sequences, realistic building envelope, and realistic HVAC configurations and sizing.
Elias asked a question online. He asks, what is the paradigm for modeling manufacturer native controls?
I mean, there is work there. BOPTEST, I would say, is more on the system level control and less on the human level control. But that's mostly because in the building side, especially, we don't have a lot of models for that. I know there is work going on in other teams to do that. There is always a bit of an issue there with like proprietary controls, sequences and things like that. It could be, BOPTEST could be a solution because you could share a binary that does not show the control sequences, but it does show you the behavior. So honestly, it could be a good way to share such a model. But so far there are no, there is some active development, but no test cases available. But yeah, that could be a great use case for sure.
From the preceding discussion, it sounds like hypothetically, if I worked at Carrier or something like that, I could download kind of a standard test case that had a piece of equipment similar to one that I make, and then I could look at the controls and say, oh, that's not quite right. And then I could internally tweak those controls, assuming I had an ability to edit the Medallica code, right? And then recompile.
Yeah, that is very true. And some HVAC manufacturers are doing that.
Do they also then feedback to you guys? Like, I guess they probably don't want to leak what they're doing.
Yes, but yes.
Gregor asked a question online. Do you have experience with classroom deployment of BOPTEST?
That's a question for Mario.
Mario's son made the finals of the baseball tournament, so he's not able to join us right
now. I mean, I think honestly in the class, I have experience deploying BOPTEST for multiple people at the same time. Like at a conference, in a building simulation conference, we had 40 concurrent users, and there was like an online workshop. And yeah, if the internet is stable, it's a nice environment for everyone, and you can see live what people are doing. It's pretty interesting.
But the backend calculations are happening in the cloud, in an instance. And
right. The other thing you need on your computer is the internet, and you don't even need Python installed because you can just open a Colab instance. So you need internet and a browser. That's all.
How do you guys pay the cloud compute fees?
Really kindly.
Do we? Okay.
Really kindly help us a little bit. But we usually discourage the use of the cloud instance. It's mostly to play with it, see if you like it, and then you can download it and deploy yourself. Like the cloud instance that we have is it's quite heavily throttled. So you cannot train an AI or do anything like that.
Gregor asks, how does one contribute one's own emulator?
Yeah, that would be through thank you for the questions, Gregor. That would be through the ABIPSA project 2. There is one task which I lead on the test case development. And so we have periodic meetings, and we can start with an email exchange and then meet there. And then there is a common repository, and we work through GitHub with issues and requests. Yeah, you go to software developer stuff.
Another, is there a vetting process?
Yeah, so I forgot to mention that was actually very important. The test case development usually is a peer review process. We have in the course of the years, we develop like a standardized way of assessing if the model is really high fidelity, and that could be through validation with the real building data, but also there is like checklists and processes to make sure that you're modeling, I don't know, master control, like everything that's needed for the test case and it's relevant for that specific building and HVAC system should be in there. So it's a peer review process, usually with a couple of rounds before the test case is deployed. That's, I would say, to go from 0 to a fully deployed test case, which is officially the BOPTEST repository, can take 1 year, depending on the complexity of the model.
So I have a couple of questions that are going to sound nitpicky, like I'm poking at potential flaws or areas for improvement, but just know that I think the project itself is super cool, and I'm providing critique from a place of love.
That's what I'm doing.
But yeah, I mean, I think broadly speaking, the general idea, like I think if you talk to someone who has been active in kind of the AI world over the last decade or so, they would probably attribute a lot of the progress that has been made on things like reinforcement learning, large language models, also specific kind of supervised learning tasks on speech recognition or image processing, things like that. That they attribute a lot of the success in the field, I think, to having a standardized set of test cases that then nerds can compete on, right? And we can all try to outdo each other and get a performance metric that's incrementally higher than the group at MIT did, and then we declare victory and publish papers and get promoted and so on, right? I think having that social infrastructure in place is important, I think, for advancement, at least in that field of AI. And I think what we do is AI adjacent, and probably we can learn from that. And so I love BOPTEST kind of from that perspective. And I think in my research group, we'll maybe try to put in more effort to like actually benchmarking stuff that we come up with on these kind of standard problems. So I guess on that note, like, have you seen participation from people kind of outside what you might call like the IBO world, like the ASHRAE world, buildings people, etc. Like, do you ever see someone come in who's like just a computer scientist who has a new RL thing? They're trying to try it out on a robotics problem and an autonomous vehicles problem and a buildings problem, and they just like pull your stuff and use it?
Yes, the OpenAI Gym interface was developed because I forgot now it was a computer science famous summer school. I didn't do the deployment there, but it was a pretty famous one. And BOPTEST was one, like the building challenge was one of the so for sure. Like the idea here is it lowers the entry barrier. You just have APIs, which for computer scientists it's their bread and butter. And they throw random algorithms and see how big that's not great.
That was my follow-up.
Yeah.
But moving in that direction, I think that's great. And I think also maybe perhaps raises the profile of buildings problems as interesting applications.
Yeah, I think that the main issue is really the fact that it takes so long to develop a test case, and despite we have quite a bit of variability, there are not enough. That's the main point that we always get questioned.
Okay, so now I'm going to start nitpicking a little bit. So there's another question.
Yeah, they're raising.
I was just going to ask, how many buildings do you have your test case?
So the official BOPTEST repository, there are 9. Then there are others around, but those are not been through the same vetting process that these 9 went through, so they are not publicly available.
And what types of buildings are those 9 buildings?
We have a few residential buildings, a couple of commercial, light and large commercial, with hydronic and air-based systems. Hydronic systems are flow heating and radiators. Air-based systems, there is both actually are R&D and VW boxes, like classical US commercial offices. And one has detailed models also for the central plants, like heating and cooling plants with heat pumps and chillers.
Are the residential units, are those just single family homes, or do you have
yeah, they're all single family homes.
Thank you.
Okay.
So the folks at NLR sort of released Open Studio MCP to create an AI interface to essentially Energy Plus. It's amazing how cool it is.
Yeah.
So if you guys have any plans to do some things?
Well, this it's BOPTEST sits on top of that, in the sense that ideally, in an ideal world, you would use Open Studio to design your building and then wrap it up and span as many instances as you want on BOPTEST.
Yeah, but still, the whole concept of how you interact with these tools is going to maybe change, right?
Yeah, no, we are working on that too. But like with BOPTEST, Professor Burgess did show that you can interact with APIs, and that's pretty straightforward to integrate them with NLM, because they are already deployed as standard Open APIs. So any LLM, you plug them in there, and they are gonna work in natural language already. So to interact with BOPTEST, it's already pretty easy with LLMs. To develop a test case for BOPTEST, that's where we are working on, in trying to combine all the tools, including Open Studio.
Yeah, I think it goes, just to press a little deeper, after I dug in a little bit, I think it goes a little bit deeper than just having the API interact with the LLM, because the MCP also learns its intelligence about how to interact with the model. Like when you ask it a vague question, like what it actually does to figure out what to do to answer your question, is like that intelligence gets learned inside the MCP, which is very cool.
Oh, cool. Yeah, I'm not familiar with that. Take a look. Thank you.
Thanks.
Sorry, hopefully this is a quick one. Is there any effort to make the interface simpler? Like, I'm kind of imagining facility managers trying to learn more about how their buildings operate, asking them to download Docker and like run that, to me, like a web interface.
Well, the one that I was showing here, so we
like if it's just a binary.
So the interface, we do have the backend interface. Someone will have to deploy it as web service. If someone has deployed it as a web service, then it's fairly simple to interact with it, but someone will have to do that for that.
Gotcha. Okay.
Sorry, Kevin, you said you had.
Yeah, one I guess ties in a little bit with the kind of manufacturer control sequences and things like that, but it's kind of an architecture, control architecture question. So I think often in the buildings world we think at a supervisory level, like the manufacturers do their thing, and then we want to do NPC or RL or whatever on top of that. We send set points, and that's kind of it. And it seems like BOPTEST is probably really good at integrating that sort of architecture.
Yeah. If you're talking about system level, so as like local control loops, for example, in an air handling unit, how do you handle like all the pressure and the distribution of the flow? That's fully modeled and fully controllable. So you can control the fan set point, or you can control the actual opening.
So I can actually dig in and get manufacturer level access.
The only parts which you cannot dig in because the models are not there yet, if you have, I don't know, the control of the chiller internal logic, that's not possible. But anything that's above that, you can, in most test cases. Yeah.
Cool. And then I guess my second, I'll stop here, is so in this kind of like race, the sort of like AI world, right? Race for performance improvements. If you beat the group at Harvard, then you declare victory and publish a paper or whatever. The metrics that we define, like I think if you give geeks a number and then you say, okay, make number good, like then we laser focus on that number. So I guess I would just say right now, my perception, and this is building on the last couple of IBO workshops and a lot of conversations that we've had over the years, is that the bar that we need to clear for performance is not like 0.1% better energy efficiency or something like that. It's like an order of magnitude reduction in what it takes to get an algorithm that does pretty well out into the world, right? So, like, is there anything in the performance metrics that reflects that? Like how much effort that people are putting in to actually get an algorithm to interact well with BOPTEST, right? And could you make a challenge around that?
Yeah, I think that's a great question. At the Adrenaline project, a little bit that the competition was already with that, a little bit with that spirit.
So they have like a limited time to like.
They had a limited time to come up with the control. They had a limited data set. They could not explore whatever they wanted. And in the actual the challenge that was scored, they only had one run with their controller like it was a real building. So they had 1 week to run the controller one time.
And they didn't see that week beforehand.
And they didn't see the week beforehand. So you can do things like that, I think, to help this evaluation process. Now it's not formalized or standardized. But yeah, that could definitely be an avenue that can help in that direction. But
I'm just thinking of that like list of the things that get reported, and it was like gas use, electricity use, etc.
Yeah, those are typical KPIs. And even for this competition, actually, it was very hard for the people that did the testing to find one score. In the end, they had one number, like you said. So even with the simple metrics, you prioritize comfort, you prioritize cost, because it's a Pareto optimization, so there is no optimal solution in a strict sense.
I wonder if we could report something in there that was like amount of interaction that was needed before you stabilized if you're doing RL or something, or like data set that was downloaded before this control performance was achieved, or the duration between like download and finish or whatever. Something to reflect like.
For sure. No, once I guess people will start to interact more with the dashboard, so we have that data available. That definitely something that we measure. For now, if you download it on your computer, then we lose access to what people are doing, right? So it's hard to with those KPIs, but more public context, yeah, that makes sense. Thank you, everybody.
Okay, well, that was great. Thank you all for the interesting questions, and thanks, Ettore, for a great presentation. I think we'll wrap up there. We'll do about an hour for lunch and start up again around 1 p.m. Eastern.